Hello everyone, my name is Pablo Fuentealba. I am from the Faculty of Pharmaceutical Science and Chemistry from the University of Chile. And today I will talk about white light emission, mainly from coordination compounds to luminescent flexible material, that is our work. As we all know, lanthanide-based materials have received great attention during the last decades, mainly due to the proven application that these materials have shown, as in light-emitting devices, bioimaging as contrast agents, optical fibers, among others. Today I will talk about light-emitting devices, as the white light emission problem is global due to the waste of energy that the common system leads. So we are focused in the development of white light emitters based on the chromatic approaches that are shown in the board here. There are different chromatic approaches, and we are using mainly dichromatic approaches based on blue emitting ligands combined with yellow emitting cation as dysprosium, or combined with green or red emitting cation as are terbium and europium species. So by this combination of the different components, the aim of our work is to develop single component white light emitters. So we are developing different ligands and the corresponding complexes, and we are performing the analysis of the optical properties of the obtained materials. Today I will talk mainly about these tripodal ligands and these Triazole-based ligands that have shown the most promising results so far. I will begin with these tripodal ligands. First, with the dichromatic approach based on the dysprosium complexes, this ligand leads to dinuclear complexes as shown in this scheme, and we're working with different substituents, methylene group, chlorine group, methoxo group. So we are modulating the ligand based on mostly the excited energy levels of the ligand that I will show later. The structure of the different complexes is obtained by single X-ray diffraction, and we can see the dinuclear species, the bridged with these phenoxo groups, and with the most important thing, as this ligand with the different substituent leads to similar complexes, and we can see here the methyl group or the chlorine group. So actually we're comparing similar complexes, but analyzing the effect of these substituents in the optical properties. Here we can see the emission spectra at the right and the excitation spectra at the left, monitoring the most intense band that will be 575 nanometers. In the excitation spectra, we can see a broad band here attributed to the ligand. This band will imply that we are in the presence of the antenna effects, by meaning that we are exciting the ligand in this band, and we are observing the narrow emission bands from the dysprosium cation. In the different complexes, we can see that these narrow bands are accompanied by this broad band attributed to the ligand. So we can see here the blue region attributed to the ligand and the yellow region attributed to the dysprosium cation. We're analyzing these measurements in room temperature, but also as functional of temperature, so we can see that this component is stable and it's possible to use them in different devices. We can see that these bands are permanent in the whole temperature range without a significant modification of the intensity or position of the bands. Now, with the corresponding emission spectra of the whole species, we are able to calculate them chromaticity coordinates for all the samples. And we can see here that all of them, the emission observed is close to white light emission due to the dichromatic effect of the blue contribution of the ligand and the yellow contribution of the dysprosium cation. So in this case, we have developed 4 complexes that actually actuates as single-phase white light emitters. When we have done this with the other cation, terbium cation, similar substituents, we have observed the formation of the same complexes, similar structure again, dinuclear species, bridged with these phenoxo groups. So we are obtaining the same complexes beside of the present cation. And the most important part in this thing, that in this case with the terbium-3 cation, the emission spectra is dominated exclusively by the emission bands of the terbium-3 cation. We do not longer observe the broad band attributed to the ligand. This will imply that in this case, the energy transfer pathway of the ligand from the ligand to the terbium cation is more efficient than in the dysprosium complexes. As we can see in the dysprosium complexes, the ligand retains some of the absorbed energy and emitted itself. In this case, most of the energy absorbed by the ligand is transferred to the terbium-3 cation, and therefore we observe mainly the terbium-3 emission bands. We have done again this as function of temperature. We didn't observe the emission ligand in the whole temperature range, and the emission bands due to the terbium-3 cation is stable in the whole temperature range. As we have seen, the different substituents, we are modulating also the efficiency of the energy transfer and therefore the quantum yield of the different complexes. The most emitting system will be with this substituent achieving a quantum yield close to 17%. And as in this case, we are only observing the emission band due to the terbium-3 cation, all of them, the chromaticity coordinates leads in the green region. But what are we doing essentially with these different substituents? With this different substituent, what we are doing is modulating or tuning the excited energy levels of the ligands by meaning of the single excited state and the triplet excited state. The most common or the most accepted pathway to achieve the indirect sensitization of the lanthanide cation is the energy transfer from the triplet excited state of the ligand, transferring energy to one of the excited state of the lanthanide cation. So by modifying this substituent, we are actually tuning this excited state, and therefore we are optimizing the energy transfer pathway to the lanthanide cation. In this system, the most emissive system was complex 4 with this substituent, achieving almost 18% of quantum yield. And the most important thing, as we are observing exclusively the terbium emission, we have a color purity close to 100%. So this is a pure green emitting system. On the other hand, with this triazole-based ligand, we have done similar work, developing similar ligands, but with different substituents in order to optimize the energy transfer pathway from the ligand to the lanthanide cations. Peer results are shown with the dysprosium cation by meaning of the chromatic effect again. And in this case, we are observing the broad band due to the ligand and narrow bands due to the dysprosium cation. By calculating the chromaticity coordinates, once again, in this case, exclusively with the chlorine substituent, we are almost in the pure white light emission. In the case of the methylene group, there is a small contribution or variation, excuse me, with the temperature from room temperature in white light to hot temperature, leading to almost bluish color. This will be explained as we are heating the system. The ligand increase its emission and therefore shift the emission towards the blue region. We have done this work also with terbium cations, and European cation. So far, we are able to calculate the quantum yield with the terbium species. And in this case, the terbium with chlorine group, we have increased the quantum yield close to 21%. And it's important to remark that these terbium species are efficient in the antenna effects as we do not observe emission from the ligand. So we are improving the energy transfer pathway towards the terbium-free cation. In the case of European species, there is another important remark. In the case of European with chlorine substituent, we have a good antenna effects as we do not observe the emission from the ligand, but with the methylene group, we observe these broad bands in the blue region corresponding to the emission of the ligand. So in this case, the terbium-3 species are pure green emitters. However, in the European species, a remarkable shift is observed. As in the chlorine substituent, we observe only the emission band due to the European. The observed color in the chromaticity coordinate is red, as expected for European emission. But on the other hand, the complex with the substituent with methylene group, due to the presence of this broadband in the blue region, the emission is shifted towards the blue region. Yeah, so we are in here, we are combining the blue and red emission, and in this case, pure red emission due to the European cation. So in all the obtained systems, as we are seeking for an application in solid state, we are preparing thin films doped with these lanthanide complexes. We are working on these polyurethane films that we are obtaining by slow evaporation films, and we are analyzing the optical properties of the obtained films. Polyurethan matrix has these carbonyl groups and imine groups that are able to coordinate with lanthanide cation. I will show mainly results including pure nitrate salt into the polyurethane matrix or this microcyclic complex into the polyurethane matrix. The presence of these multidentate ligands prevents the interaction of these terbium species with the possible coordinated groups from the polyurethane. These skeleton ligands will prevent the interaction. However, in the case of the nitrate salt, we have observed that these nitrate and water molecules are labeled from the metallic center and therefore can migrate. And in this case, we have observed some interaction of this terbium-3 species with the matrix. This is revealed by the infrared spectra. Here in black, we have only polyurethane film. In blue, we have the lanthanide species, and in red, the obtained film. We can see in here that in the case of the terbium nitrate species, we can see a decrease in the vibration band of the amide 1 group. And we can see the appearance of this second band that will be the coordinated group of the polyurethane matrix. And we can see also for sure some vibration bands due to the macrocyclic complex. In the case of the complex with this skeleton ligand, we do not observe this decrease in intensity of the amide 1 group. Therefore, we are concluding that in this case, there is no coordination effect from the matrix with the terbium-3 cation. This will be like a solid state dispersion. In this case, we do observe an interaction between the terbium cation and the polyurethane matrix. So we can see that when we have this skeleton ligand, the coordination of the terbium will be focused on this skeleton ligand, we being not able to coordinate the polyurethane chains. But if we have these labeled ligands, it's possible to interact the lanthanide trication with the polyurethan chains. So we are obtaining different systems considering the ligands present in each complex. The most important part of this research is that we are increasing considerably the photophysical quantum yield of the bulk complex onto the thin films. This quantum yield, close to 60%, 16%, is obtained with the complex that in bulk was only 20%. So we're multiplying the quantum yield by a factor of 3 when preparing these thin films. So we are developing flexible material, increasing the quantum yield by doping this polyurethane matrix with the different lanthanide-based complexes. Finally, to acknowledge the different financial support that we are receiving from Chile, from different Fundesit projects, and from Brazil, from different agencies. To acknowledge the different researchers from different universities, from Universidad de Chile, from Universidad Andrés Bello, both from Chile, and from Universidad Federal de Goiás, from Brazil, that help us with the optical measurement. Finally, to introduce to you our research group from Chile, from Brazil, our collaborators from France, and also the University of Sao Paulo. Thank you. Bye.